All right. So tonight we're going to talk, section 3.2, of course. Okay. And the idea here is it's, some just in the very basic derivative rules. Okay. But the cool thing about these derivative rules, okay, is that they are limit laws. So everything we do with derivatives is just a limit law. So in a minute, we're going to start running through them, and you're like, oh, that's really easy. And they are. So my first one is this. If you want to take the derivative, we write it this way, the derivative of a linear function, so just something like kx, what's the rate of change of a linear function? It's just the slope. That's it. That's it. What's the derivative of some constant function? How fast is a constant changing? Dude, it's not changing. That's a constant. Well, you're like, wait a minute. I feel like if I did this, I could then take the derivative of y equals mx plus b. Well, this is a linear function. And my first thought is well, wait a minute now. The rate of change is just m. I learned that in Algebra 1. And you're right. But this brings up something interesting because a derivative is just a limit. And the limit of the sum is the sum of the limits. That's also true when it comes to derivatives. I can take each piece and look at it individually. And what is the derivative of a constant? 0. And what is the derivative of that? Just m. So my answer is just m. Is that true for minus? Well, of course, plus or minus, right? That was also true when we did limits. Okay, the sum or difference of a limit is the sum or difference. The limit of the sum or difference is the sum of the difference of the limits, right? That's what we said. It's just the same thing here. A power rule. This is a big deal. The power rule says this. If you want to take the derivative of, well, actually, let's just do power rule. So x to the n, the answer is n times x to the n minus 1. That's it. So what's the derivative of x squared? Well, it's just 2x to the first power. That's all. What about the square root of x? It's a great question. What about it? Well, that's the same as taking the derivative of x to the 1/2 power. So that would be 1/2 x to the minus 1/2, or 1/2 square root of x. Okay, pretty straightforward. Now, some other ones that come up. Some other ones that kind of come up, and we'll do them as we get to them. But what's the derivative of e to the x? Well, the derivative of e to the x, I need a function that describes the slope of this function. I need a function that's very small positive slopes over here, because these are positive slopes, positive slopes, positive slopes. There's a tangent line. Here it's about a 1. And then here it starts going up like a crazy person. Can you think of a function that looks just like that, or that looks like it describes the shapes of those tangents, or the shapes of those tangent line slopes? And the answer is, it is its own derivative. Okay? Well, what about the derivative of the natural log of x? Well, what about it? Well, here's natural log. It looks like this, yes? All of these slopes are what? Positive. And the further I get out this way, they're kind of petering off, but they're still going uphill. They're still positive slopes. Can you think of a function that has really steep positive slopes and then starts getting smaller and smaller and headed towards 0 values? Well, I can. It looks like this. And you're like, that kind of looks like 1/x, Jay. It does. And in fact, it is. Now you're like, well, 1/x is over here too. You're not wrong. But by definition, the ln of x has a domain of x is greater than 0. So its derivative will share that same sort of domain. In other words, it will not show up over here at all. Okay? Cool. So yeah, that's neat. What are some other ones it gives us here? Sure. Ooh, here's a cool word. Continuity. We talked about this before, right? What does continuity mean? Continuity means when you have a function, and here it is at x equals a, what must be true? First of all, f of a must exist. So I can't have a hole here. Number 2, the limit as x approaches a of f of x must exist. So what does that mean? It means no asymptotes, no holes, no jumps. So this one works. And number 3, the limit as x approaches a of f of x must equal f of a. That is, in other words, the limit, which appears to be right here, must equal the actual value. Okay? So we know that. Today we're going to learn a new word which is called differentiability. Differentiability. There you go. Boom, 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 boom. And of course this means what? That means the derivative exists there. Interesting. What does that mean, Jay? Well, it means this. So, for instance, let's do a nice linear function. Boring. Right here at x equals 2, does the derivative exist there? Well, I don't know. How would I know? Does it have a rate of change right there? Well, sure. Anywhere you go around here, the slope is whatever the slope is. The derivative exists there. Well, the only way for the derivative to exist there is if the function's continuous. And so there is a rule that says this. If a function is differentiable, or in other words, differentiability, we say differentiability implies the function is continuous. So if I tell you that it's differentiable, you know the function is continuous at that point. Now, there are some functions like this guy, 1 over x. It's a very, very handy function. It's a very wonderful function. We know that x does not equal 0, obviously. It doesn't exist there. So tell me, what is f prime of 0? Of 0. And the answer is, it does not exist. The derivative doesn't exist there. Because remember, the function doesn't exist. It's really hard to get a rate of change if it just quits existing. So because the derivative doesn't exist, that implies what? The function's discontinuous there. But if I can find a function that is differentiable, I don't know, square root of x, and again, this sucker is differentiable everywhere, pretty much along here. Let's say at x equals 4. Does it have a slope at x equals 4? Well, yeah. So here's x to the 1/2. That's f of x. I just did this on the previous page, so that's what it is. And then of 4 would be 1/4. This exists, and it implies that this function is continuous there. I would like to talk about this for a minute, though. What happens here? The function, it just bursts onto the scene right there, right? And if I asked you what is the limit as x approaches 0 of the square root of x, you would say it does not exist because you cannot come at it from both sides. Therefore, the limit does not exist. And so you'll recall that we got around that by saying the function is right continuous. That is, you can approach 0 from the right and get a perfectly good limit. And everything is hunky-dory as long as you stay on this side of 0. But here's my question to you. Does f prime of 0 exist on this guy? And the answer is no. because it's going to be 1 over 2 square root of 0 to 1 over 0. That's a problem. But if you think about it, it makes perfect sense. When x was less than 0, wait a minute, x cannot be less than 0. What was y? Yo, I don't know. It wasn't anywhere. And all of a sudden at 0, boom! All of a sudden you've got the y is equal to 0. How fast did that change? Instantaneously. And if you think about it, what is slope? Slope is change in y over change in x. If the change in x is 0, that means it happened instantaneously. Okay? Well, what does that mean? It means you have an undefined slope. In this case, we just say, hey, look, the derivative does not exist. Or in other words, it is not differentiable at x equals 0. Or maybe an easier way to say it is that square root of x is differentiable when x is greater than 0. The only place it's not is at x equals 0. Okay? So this is are you talking to a good kid or a bad kid, you know? If you're telling a bad kid what he can't do, that list is as long as your arm, it's easier to tell him the one thing you can do. If you're talking to a good kid, well, it's like an infinite number of things he can do, and there's like one bad thing you don't want him to do. Okay? So you can either tell me it's not differentiable at 0, or you can tell me it's differentiable anywhere greater than 0. They're telling me the same thing. Okay? And I'm perfectly happy with that. Okay? Here's a few problems from the assignment. It's a very straightforward deal here. You'll see something like this. Hey, find the derivative of this guy. Oops. Of this guy. Check it out. When t equals 5. I don't even know what that means, Jay. Let me help you out. This says take the derivative. This says after you've taken the derivative, slap a 5 in for t. So the power rule says you bring that down, and then you subtract 1 off of that guy. Now be careful. That's negative 3 halves minus 2 halves, so it's negative 5 halves. And so now, if you will, if we had this was f of t is t to the minus 3 halves, then this is f prime of t then, isn't it? So then what is f prime of 5? I don't know. Oops. Okay. And, you know, whatever. It is what it is. I think if it's me... No, I don't know. Let's just do it. Let's do the calculator. It's too late tonight, and I can't think anymore. So, negative 3 halves, 5 to the negative 5 halves. So, negative 0.0268. Negative 0.0268. Now remember, what does that mean to me? That's a slope. Where is that a slope? When t is equal to 5. So let's go graph this function. Let's graph x to the parentheses negative 3 halves. Okay? And right there you see 5. Hey, what's the slope right around in there? The slope right around in here is basically 0 slope, isn't it? It's a very small slope. Remember, those numbers, I can take some of those numbers, I can find some slopes with them, some rates of change. But in reality, it's not much of a slope across there. That's pretty flat. And what we just found is the slope is something like that. It's negative, because obviously it's going down, but it's basically a 0 slope. It's not changing very much at all. Okay? Here's the situation. You might be asked to find if f of x is equal to 3x, x plus 1 squared, and find f prime of 2. Well, first of all, I'm going to find f prime of x. Thank you very much. And so, how to do that? Well, first things first, I'm going to rewrite the function. So I'm going to FOIL this out. It's going to give me x squared plus 2x plus 1 times 3x. That's 3x cubed plus 6x squared plus 3x. And all I've done thus far is rearrange things. Now, take the derivative. Remember, when I do this, oh, one more thing. I almost breezed over it. I'm sorry. Let's write this down. What if you had a constant times some function? The derivative rules say you can do this. Why can you do that? Oh, that's a limit law. Remember, if you have a limit of a constant times a function, you can pull it out. That's the same thing. So right here, I can ignore this 3. I can just leave it like this, and then look at the power rule. That's going to be 3x squared, like so. Other people just prefer to think of it like this. 3 times 3 is 9x squared. It's the same deal, but it is one of our limit laws again. That's all it is. The derivative of a linear function is just the slope. So this is 9x squared plus 12x plus 3. And then if I want f prime of 2, that's 4 times 9 is 36 plus 24 plus 3, that's 63. Right? It's a pretty easy deal. We could do these, pretty much all night. What you'll end up doing pretty much on this whole assignment is taking derivatives and then evaluating them. So it's not terribly difficult. Okay? This one's a little trickier. Don't panic. dy dx just simply means if y is this function, to take the derivative of it. It's exactly the same thing as doing this. 2e to the x plus 6x minus 3. It's the same as saying, hey, go find f prime based on that guy. It's the same exact thing. This is Leibniz notation. It has a place. This is Newton's notation. I dig Newton's notation. It makes me happier for most things at this level. Later on, I like Leibniz a lot for other things. So let's take the derivative. What is the derivative of e to the x? Why, it's e to the x. What do I do with this constant? It just tags along for fun. What is the derivative of 6x? It's 6. What's the derivative of this constant? It's nothing. So I have f prime of x. I want f prime of 4. Okay? And that's too much work for this late at night, so I'm just going to type it into my calculator. And I'm going to get, 2e to the 4, right? And then what else was it? Plus 6, minus 6, plus 6, plus 6. Come back. So my answer is 115-ish. So my slope is 115. Does that shock me a lot? It doesn't, because e to the x goes up like a bat out of heck. Times it by 2, it's going to go up twice as fast. Add 6x to it, it's going to go up like a crazy person. Subtract 3 doesn't really do much to it. Okay? Now, one thing I would like to mention in this chapter, and I think we breeze over it a little bit sometimes, y is a function of x, right? That's what we've said all these years. We said y is a function of x. Okay? Well, if you think about it, the slope of the tangent line, which is a fancy way of saying derivative, will change based on where you are on the graph. Meaning that f prime is also a function of x. That is, the slope, or if you prefer dy dx, or if you prefer delta y over delta x, the change in y over the change in x will depend on where you are on the graph. Now, think about that. Right in through here, from here over, we've got positive slopes. So right here at x equals 7, for instance, it has a certain positive slope. It's a different slope than if it was right off the bat, right down here at x equals 2.1 or something. Right there. That's a positive slope, but it's a smaller positive slope. Between here and here, why, we had negative slopes, yes? And from here this away, we had positive slopes again. And the idea is that, hey, f prime is a function of x. This is the biggest reason why I like Newton's method better, because it actually makes a little sense. Like, what does it mean when I take f of x? It means what's y when x is this and such. When I say f prime of some value, like f prime of 3, I want to know what is the slope when x is 3. Okay? And that's kind of a thing that doesn't get mentioned a lot in this chapter, but it's kind of a big deal, and I think a person should be very comfortable with that thought process going forward.